So we should be on activity 7. We are going to do compound probability for data displayed in two-way tables. So we're going to just talk about different ways of displaying this. So these are going to be the things that we want to make sure that we get through. Remember, vocab is very, very important for statistics. So when playing a board game, it's common to roll 2 number cubes and calculate their sum. So how many different outcomes are there? How many events are there? 2 events. Rolling 1 cube and rolling a second cube. How many outcomes are there for the first cube? How many are there for the second cube? And 6 times 6 is... And then if I wanted to write a sample space for rolling those, I would go, okay, what are the possibilities? You could roll a 1 and a 1. You could roll a 1 and a 1 and a, and then you could go, okay, finish all the way till you got 1 to 6, yes? Then you go 2 and 1, 2 and 2. And if you did that, it would look something like this. Alright, so if I made the list, it would look something like this. Yes? Now, a two-way table shows the relationship between 2 data sets. One data set is organized in rows, and the other is organized in columns. So it says complete the two-way table representing all the possible what? Sums. So what's going to be going in these boxes? So what's going to go here? 2. What's going to go here? You with me? And you could fill this whole thing in, and if you did, it would look, bless you, it would look something like this. Make sense? The sums. What does sum mean? Add them up together. So 1 and 1 is 2, 6 and 6. So what are the possible sums? 2 through 12, correct? Okay. Now, please understand what this is telling us. We have to go back to geometry for just a minute. Some of you are having nightmares. Some of you are like haranguing inside. Yeah. Just for a split second. Converse. Yeah. Okay. If I said an if and a then, when I do the converse, I switch the if and the then. So, in first period, they were asking me about my dog, so I talked to them about shaving my dog. And they're like, why'd you shave him? Because my dog had this skin infection. So, basically, the doctor has a thing, and he goes, if a dog has a skin infection, then shave the dog. Correct? Makes sense, right? So switch those. If a dog is shaved, then he has a skin infection. Is the converse always true? No, and that's what happens, and that's what you studied in geometry. Sometimes when you switch the converse, it's true. Sometimes it's not true. We had a contrapositive. Do you remember that? Where you switch it and you make it the negative. If a dog does not have a skin infection, then you do not shave the dog. And then there was one where you switched them both, and you were like, if a dog is not shaved, then it does not have a skin. You did all. There was 3 different things that you did with it. You could switch the if and the then. That's what we did. That's what we just did. That's converse. You could just take it and put not without switching it. Then you could switch it and put not. Those are the 3 different ways that we could come up with. You guys understand what I'm talking about? Yeah. And if they were all true, then you could make it an if and only if statement. Okay? Now, what happens with this is we are doing the converse of what we've talked about. Chris, here's what we have talked about. It says you learn that if 2 events A and B are independent, that's my first criteria, then what were you able to do? the probability of both events occurring together, meaning A and B happening, you could just take the probability of A and multiply it by the probability of B. Do you guys remember what I'm talking about? The converse is also true. That means that if I tell you that the probability of both events occurring, A and B, if I tell you that probability is A times B, then what do you know about the two events? They are independent. So, use the converse to determine if these events are independent. A result of 3 on the first number cube and a result of 3 on the second number cube. So the way we're going to do this is we're going to count in real life how many different ways is that possible. Then we're going to find the ways that it's possible for A event. We're going to find the ways it's possible for B event. We're going to multiply them, and we're going to make sure that those two are the same number. Here's what I mean. How many different ways, if I go up here, is there of having a 3 and a 3 together? 1 out of, so I should have a 1 out of 36, correct? What are the chances of me rolling a 3 for the first number cube? 1 out of 6 chance at rolling 3. Because how many numbers are there? 6. How many 3s are there? 1. So I have a 1 out of 6 chance. Sage, you're looking at the whole population. Yes, it's 6 out of 36. What is 6 out of 36 reduced to? 1 6. Same thing. What are my chances of rolling a 3 on the second number cube? 1 out of 6. They're not. There's second dice. How many different 3s are on the second dice? 1. How many numbers are total on the dice? 6. So I still have a 1 out of 6 chance of rolling a 3 on the second cube. Does that make sense? What is 1/6 times 1/6? What did we do when we counted it? We got 1 out of 36, correct? What did we do when we multiplied it? We got 1 out of 36. What does that mean for us? These two events are independent of one another.
Wait, so if it's the same when we count it and it's the same when we multiply it,
Yep.
they are converse?
They are independent of each other.
Okay.
What happens if I count it and it's not the same as when I multiply? Then they're not independent of each other. Does that make sense? So you should be trying this. So a result of 2 3s and a sum of 6. How many times does that happen? 1 out of 36. There's one time that there's 2 3s and they both add up to 6. There's only one time that happens up there. Does that make sense? Yes? Now, what's the chances, what's the results of 2 3s? 1 out of 36. What are the chances of a sum of 6? You have to look at your chart and you're going to have to count. 5 out of, and so what did they do with those two things? They took 1 out of 36 and multiplied it by 5 out of 36, and when you get that, you get this number. Are these two the same? No. Is what I actually, real data, the same as when I multiplied them? No. What does that mean? The events are not independent. That's the only thing that we are going over.
What does it mean if they're independent? Like, just like...
That the first event has no really effect on the second. Does that make sense?
So the difference between both converses is that one of them you're just multiplying the two probabilities. The other one is when.
So again, make sure we are understanding this. The first thing I taught you at the beginning of this week was I said, I will tell you that these two events are independent, and if these two events are independent, then you know that the probability of A times the probability of B, that has to equal the probability of A and B happening. So in the beginning of the problem, I tell you they are independent. You can then use this. What we are doing today is I'm not telling you if they're independent. I'm not telling you if the probabilities are true. What you're checking is you're saying, does the probability of A times the probability of B, does that really equal, you are questioning this, does this equal the probability of A and B? And we are looking at our charts, we are checking it, and if it is true, then we know that they are independent of each other. If they are not equal, then I know they're not independent. Does that help with this out? Okay, so let's make up, because I don't like their last couple that they do. We're going to go through them quickly. It says a result of 6 on the first number cube and a sum less than 7. Okay, think about this. If you get a 6 on the first number cube, you're starting off with a 6 when you add, right? And when you, what's the next, so lowest number you could add to it? A 1. And what's 6 plus 1? Is 7 less than 7. So is this possible? So what should be my result when I do this up? It should be 0 out of 36. Not 0 out of 0. Don't be throwing that around. That's nasty. 0 divided by 0 is oof. People are still studying that. It's not undefined even. It's an indiscriminate form. People are studying that number. There's 6 of them. Okay, 6 really, really weird numbers that we don't even know. Yeah. So anyways, 0 divided by 0, no good. So what happens? This should result a 0 out of 36 chance of happening. There is no way this could happen. You with me? But if I do the math and I try, what's the result of a 6? How many ways is there get that happening? 1 out of 6, and I should times that by what's the result? How many are a sum of less than 7? If you count it, I believe it's 15 out of 36. These guys can reduce, and this becomes a 5 and a 12. And when you get that, it becomes a 5 over 72. Yes? Does a 5 over 72 equal 0 out of 36? So, do these things equal each other? So what does that mean for me today? These two events are not independent. Sure, yes, but all we're saying is not independent. How does that confuse you? No, it's not. Not necessarily because, right, it's not about, it just means not independent.
It just kind of makes you think, like you have to think.
Just understand it's not independent. That's all because they're asking, is it independent? No, it's not independent. If I pointed over to, and I said, is that a dog? And you go, no, it's not a dog. Does that weird you out? No. Why is it me going not independent?
There's a word for not. Yeah.
I'm going to be careful.
It's not.
All right. A result of any number. Let's not get into this. A result of any number on the first cube and a sum of less than 7. Okay? What are the chances of getting the first number on the number cube? 6 out of 6. Right? You're going to get a number. What in the sum of less than 7? 15 out of, which reduces to a 5/12. If you count this up, you should get 5/12. Yeah. it should be 5/12, right? They didn't reduce it. I don't know why they didn't reduce it. 3 goes into this. Okay? So, are these two equal? Yes, because when you multiply it out, you get the same thing as you did in the beginning. So what does that mean for us? They are independent. Makes sense. Not dependent. Oh, throwing that out there. Really freaks some people out. Alright, does that make sense? Here's what I made up another example, because theirs I feel like are not great to help you out. What if I said, what are the possibilities of rolling a 2, and a sum of less than 7? How could I use these two charts to help me figure that out? Well, what I would do is, if I said rolling a 2 first, then I know that it's this line that I only have to concern myself with. Does that make sense? So when I come down to here, I'm going to go, okay, this is the only line that I need to worry about, and I want only the ones that are less than 7. Yes, 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 no, no. So how many are there? Should there be 4 chances out of 36, which were reduced down to 1/9. You with me? Now, if I wanted to see if they're independent, I would go, what are my chances of rolling a 2 on the first number cube? Would be 1 out of 6. Multiplied by, what are the chances of me rolling it and adding them up to less than 7? We said it was 15 out of 36. You with me on that? When we reduced this became a 5, this became a 12, and I multiplied it and it became 5 out of 72. Does this number equal that number? No. So what does that mean? These guys are not independent of each other. With me?
You say they're not dependent, does that mean that they're dependent?
I think that's what we just went through that.
Sorry, I'm just thinking a lot.
That's okay. We are. Go. Here we go. So does that make sense of what they were trying to accomplish in this section? All right, frequency table. Frequency table, we can move a little quicker, I think, through this section. Shows the frequency an item, number, or event appear in the sample space. So they're going to ask you to complete this to a table. So when you go to complete this table, what are the outcomes that can happen on this? And this is the sum of the number cubes. So what are some of the sum? 2 through 12. How many times does 2 appear up there? That's what frequency means. Frequency is how many times it occurs. So how many times does it occur? 1. How many times does 2 occur? I'm sorry. 2. My fault. 2 is over here. How many times does 2 occur? Once. How many times does 3 occur? Twice. And if you fill this out, it should look something like this. Not always will they have a pattern. You should count it out to make sure. If I add these all up, how much should they add up to? Because there's 36 different outcomes, so this should account for all 36 of them, right? This tells you that if you wanted to see how many times 7 was added up, it would be 6 times. Does everybody understand this frequency chart? Yes? Now, how can I use this to predict some probability? What's the probability of rolling a 7? How many times does 7 appear? Out of? And so if I reduce that, it turns down to? So there's a 1/6 chance of me knowing that they're going to add up to a sum of 7. Does that make sense? All right, what about the probability of rolling an odd number? What can I do? Add all the odds up, which I would add. Would I add 1? Because no. Would I add this one? Why? This one is for adding up to a 2. Is 2 odd? No. So what number would I start adding with? This 2, because 3 happens twice. You with me?
3 is odd.
3 is odd. So I'm going to add 2. I would add 4, I would add 6, I would add 4, and I would add 2. And when you get that, what do you get?
18 out.
And so 18 out of 36 really reduces to a 1/2. Does it make sense on how we use this frequency chart? Okay, if you wanted to do what is the probability of rolling a sum less than 7, you're going to go back up to the chart, and what are we going to add together? From the numbers here and up. Why? Because all these sums are less than 7. So you're going to add 5 and 4, which is 9. Add 3, which is 12. Add 2, which is
14,
and add 1 is
15.
out of 36, which reduces down to 5 twelfths. Good? Frequency chart seems all right? All right. R says that the probability of passing a true or false test is always 50%. I'm not trying to read that. Is she correct? Let's investigate by considering a true-false with 4 questions. So they're going to list all the ways that you could answer a 4-question test. Use checks to represent a correct answer and X. So does everybody understand how they make this list? Okay, so they make this list. They go with all truths. They go with 3 truths, and then they how many questions does this person miss in the beginning?
0.
0. How many does this person miss?
1.
And how did they do that? Yeah, they jumped around. I would have done. I personally would have organized this different.
Yeah.
I would have done person misses, none wrong. The person misses 1 wrong. And so what I would have got is they got the first one wrong, they got the second one wrong, they got the third one wrong, and then they got the 4th one. That's how I would organize it. Then I would do all the possibilities of them getting 2 wrong. What's the crazy thing about them getting 2 wrong? They can go in different spots and getting them different, if you miss 1 and 2, that's different than missing 1 and 3, which is different than missing 1 and 4. Then you could miss 2 and... Did I already do 1 and 2? Did I already do 1 and 2? Yes. So doing 2 and 1, is that the same scenario? So I don't have to count it twice, yes? All right. So create a frequency table that says the number of correct that they got. 0 correct or answers correct, there's only 1 time. All 4 correct, there's only 1 time. 1 number correct, there's 4 of those. 3, there's 4, and 2, there's 6. Does that make sense? All right. What is the probability that a student who guesses on all 4 questions will pass the test, assuming a grade of 60% or higher is a passing grade? How many would you get correct? What chance do you have of passing that test? 5 out of 10, 15, 16. So you have a 31.25% of passing that test. Does that make sense? So is she correct? No. Because you don't have a 50%, you have a 31% chance. All right, we'll stop there. We'll start on problem 3 tomorrow.